This is a video for AQA Further Pure Mathematics. Calculus section 2.4, where we're looking at improper integrals, where the integral crosses a value where the function is undefined. As an example of this then, consider the integral from 0 to 3 of 1 over x minus 1 all squared. We can see that when we get to x equal to 1, there's an asymptote because the function is not defined for x equal to 1. So our integral that we're trying to evaluate actually goes across this. We know that the function itself is increasing indefinitely, but what about the area? From the graph we can't really tell, so what we need to do is to consider a limit. In fact, what we do is split the integral into two parts. One from 0 up to a value a, and the other from a up to the other end of the limit, which is 3. So we consider this in two parts. One part from 0 up to a point a of 1 over x minus 1 squared, and the other one from a up to the top point 3 of 1 over x minus 1 squared. We can then look at the limit as a approaches that problem value 1 of each of these, and add them together. So we can say that those are then equivalent to taking the integral from 0 to 3. Well, the integral itself becomes 1 over x minus 1 and then multiplied by negative 1. So we get negative 1 over x minus 1. And we need to evaluate that between 0 and a and take the limit as a approaches 1. And similarly for the other one, it will be the limit as a approaches 1. Again, negative 1 over x minus 1. This time evaluated between a and 3. So we then have the limit as a approaches 1. Putting in a into bracket, we get negative 1 over a minus 1. And then putting in 0 gives 1, so we get minus 1. Second one, the limit as a approaches 1. And putting in 3 into here, we get negative 1 over 2, and then plus 1 over a minus 1. But 1 over a minus 1 does not converge as a approaches 1, so we can say that that approaches infinity, and therefore neither of these is defined, so the value of the integral does not converge. Well, here's a second example which looks very similar, in that at x equal to 1, the function x minus 1 to the power negative 2 over 3 is undefined, so it's asymptotic. The graph is asymptotic to the line x equal to 1. But again, we can't tell from this whether we've got a convergent area or not, so we need to consider the same process where we take the limit. So splitting this integral into two parts, one going from 0 up to a and the other one from a up to 4, we're looking at the limit as a approaches 1 for x minus 1 to the power negative 2 over 3 dx, plus the limit as a approaches 1 of x minus 1 to the negative 2 over 3 dx evaluated from a up to 4. So splitting it at that problem value, a equal to 1. The integral for both parts is 3 multiplied by x minus 1 to the power 1/3. So we need to evaluate that from 0 up to a, and from a up to 4, and then consider the limit of each of those as a approaches 1. Or we get the limit as a approaches 1 of 3 a minus 1 to the 1/3, and then minus 3 multiplied by negative 1 to the power 1/3. Then we're adding to that the limit as a approaches 1, putting 4 into here, 3 multiplied by 3 to the power 1/3, and then minus 3 multiplied by a minus 1 to the power 1/3. But as a approaches 1, we can see that a minus 1 approaches 0. So in the limit then, we're left with negative 3 multiplied by negative 1 to the power 1/3, and plus 3 multiplied by 3 to the power 1/3. The cube root of negative 1 is negative 1, so this then becomes equal to 3 plus 3 times 3 to the power 1/3. So in this case we've got it converging to a value, even though we had a problem in where we had to split the integral into two parts. So the graph might well be going off to infinity, but the area is something that we can evaluate because it converges to a value. So the general method then is to take the problem value, call it a, and then split the integral into two parts. One which is at the lower end approaching a, and then from a up to the upper end of the integral. Once we've done that and evaluated the integral, we can look at the limit as a approaches that problem value. So that concludes this video on improper integrals, and indeed is the last one in the series of Calculus 2.